Hi there, in this video we'll discuss double integrals. These are also referred to as iterated integrals. We will find the volume V between a surface given by z equals f of xy and a rectangular region R in the xy plane. Here's a picture to illustrate the situation. I've drawn the coordinate axes, and you can see we have a surface z equals f of xy. Now this rectangular region R in the xy plane is the domain of our function z equals f of xy. This is the set of input values, the points that map to a point on the surface. Now I should point out we don't have to just work with a rectangular region like this. We're kind of limiting ourselves by doing that. There are other regions we could consider, but for this section, we'll just focus on a rectangular region in the xy plane. What we want to do is find the volume of this three-dimensional object formed by looking at what's trapped between this rectangular region R and our surface Z. And I didn't intend for this to be leaning so much, but I think you can at least get a visual of what we're trying to do here. So the way we'll go about finding this volume is very similar to what we did back when we were working with a function of a single variable and trying to find the area between the curve and the horizontal axis. It's this idea of a partition and sum. So that's exactly what we're going to do here to find the volume. Step 1 is to divide both intervals, AB and CD, into n equal subintervals. We'll use delta x to denote the width of the subintervals here on the x-axis. Delta x is b minus a over n, and we'll use delta y to denote the width of the subintervals along the y-axis. So delta y is d minus c over n. In setting up this partition, we end up with a collection of n squared subrectangles, which I'll denote by big R1, R2 through Rn, where this capital N is equal to n squared. So I've got the rectangular region R redrawn here in the xy plane, and you can see from our partition that we get these n squared subrectangles. So for each of these subrectangles, we're going to construct a rectangular box of height f of x sub I, y sub I, and base r sub I, where x sub I, y sub I is some point in the subrectangle. So you can think of this ordered pair x sub I, y sub I as our sample point in the subrectangle. If we go back to the picture, you can see what this looks like. So I've got a subrectangle drawn here in red. We're going to pick a point in this small little rectangular box, x sub I, y sub I, to be our sample point. And maybe for purposes of this illustration, I'll just choose this bottom right corner of this subrectangle. That will be used to determine the height of this rectangular box that extends up to the surface. So here's f of x sub I, y sub I. I chose the sample point to be that lower right corner of the rectangular box, so it maps to this point. And that's what we use to determine the height of this rectangular box. Now that we've formed all these rectangular boxes, we need to find the volume of them. We'll let V sub I denote the volume of the rectangular box above that subrectangle R sub I. How do we determine this volume? Well, we take the height of the rectangular box that's f of x sub I, y sub I, multiply by the width, delta x, of the base subrectangle, and the length, delta y, of the base subrectangle. Then we sum all of these volumes to get our approximation for V, the true volume of this three-dimensional solid. So we're going to add V1, V2 through Vn, and if you like, you can use compact summation notation to write the sum from I equals 1 to big N of f of x sub I, y sub I, delta x, delta y. This is a Riemann sum of f on R. As n becomes larger and larger, meaning we're using an even finer partition, so we have even more of these rectangular boxes, the Riemann sum becomes a better and better approximation of the actual volume V. In fact, the actual volume V is found by taking a limit, the limit as n goes to infinity of our Riemann sum. The notation we use here is the double or iterated integral. So we write the double integral over R of f of xy dA. We have an important result known as Fubini's theorem, which says we can switch the order of integration. It doesn't matter if we first integrate with respect to x and then y, or vice versa. And what I'd like to get us in the habit of doing now, since we're working with two variables, when you write the limits of integration, write x equals a to x equals b, y equals c to y equals d, just to help you keep track of which variable you're working with. So this says if we first integrate with respect to y and then x, that's why I've got dy dx, that's the same as first integrating with respect to x and then y. That's why I've written dx dy here. We start on the inside and work our way out. So let's look at this example. Find the double integral of the function xy over the rectangle R in two ways. Integrate first with respect to x, integrate first with respect to y. So we're going to be setting up the double integral over R of xy dA. And R happens to be this rectangular region consisting of the ordered pairs xy, where x is between 0 and 2, and y is between 0 and 1. I have a display of this surface xy on this rectangular region. Again, y is running from 0 to 1, x is running from 0 to 2, and you can see what this surface looks like. So what we want to do is set up a double integral to give us the volume trapped between this surface and the xy plane in this rectangular box here. In part A, we're going to set up the double integral so that we're first integrating with respect to x. So that means we should have dx dy, and x runs from 0 to 2, y runs from 0 to 1. Because we're first integrating with respect to x, we're going to treat this y as a constant. In fact, you could even bring that y outside of the first integral since you're treating it as a constant, and then you'll just integrate x like normal. Well, when you integrate x, you get x squared over 2, and that constant multiple y just tags along. Now we have to evaluate this from x equals 0 to x equals 2. So I'm going to first plug in x equals 2 to get 2 squared over 2, or 2y. And then you subtract this thing evaluated at x equals 0, well, that goes away. So we're left with 2y. At this point, there aren't any x's remaining, and we're just going to integrate with respect to y like normal. So we need an antiderivative of 2y, that's y squared, and you evaluate this from y equals 0 to y equals 1. So you end up with 1 squared minus 0 squared, or 1. That's the volume of our three-dimensional solid region. In part B, we want to set up the double integral so that we're first integrating with respect to y. So now the order will be dy dx, and because we're first integrating with respect to y, we're going to treat x as a constant. So in fact, that x could come outside of the first integral, and then you just integrate y like normal. Well, that's y squared over 2, and our constant multiple x tags along. So we'll evaluate this from y equals 0 to y equals 1. That gives us 1 squared over 2 times x, or x over 2, minus 0 squared over 2 times x, which is just 0. So we're left with this. Notice there aren't any y's anymore in our integrand, and we'll just integrate with respect to x here to get 1/4 x squared evaluated from x equals 0 to x equals 2. So this gives us 1/4 times 2 squared, or 1, minus 1/4 times 0 squared, which is 0. So we see here that we ended up with the same result as in part A, where the order of integration was reversed. The volume is 1. So the volume of the solid trapped between this surface and the xy plane in this rectangular region is 1. So that wraps up our discussion of double integrals. Thanks for watching.